Solar modules are needed to produce a certain amount of power. How would you calculate this? What is the effect of module efficiency on your result? Find out in this video. This video is part of iPolytech's online course on solar energy. iPolytech, professional development courses for engineers. Sizing a PV system involves a number of steps. The first is to determine the required PV power capacity based on the energy consumption of the load and the number of peak sun hours per day, that is at 1000 watts per meter squared, at the location in question. Let's look at an example. Let's say the annual energy consumption of the load is 9,125 kilowatt hours per year. This gives us an average daily consumption of 25 kilowatt hours per day. Let's say 50% of energy consumption will be provided by PV. So the PV system energy output will equal 12.5 kilowatt hours per day. Now determine the number of peak sun hours available per day at the installation location. There are two ways of doing this. In the first method, you look up the number of peak sun hours available per day on a map or chart such as the ones shown below. Remember to use the value of the worst month of the year for critical applications. Here we see a world installation map. This map shows the amount of energy in hours received each day on an optimally inclined surface during the worst month of the year. Or you can use tables such as this one, which shows the sun hours available per day in Canada. This table shows the number of sun hours at peak solar irradiance, or 1000 watts per meter squared, during the summer, winter, and the average over the year. Remember that it is more difficult to produce electricity during the winter because of the shorter days, increased cloudiness, and the sun's lower position in the sky. So if you are using your system primarily in the summer, use a summer value. If you are using your system year-round, especially for a critical application, use the winter value. If you are using the system most of the year, that is during the spring, summer, and fall, or the application is not critical, use the average value. Here is a similar table for the USA. In the second method, you calculate the number of peak sun hours available per day based on the global horizontal irradiation map. However, note that this method will give you the yearly average value. Let's look at an example. Here is the global horizontal irradiation, or GHI map. Remember that this map shows us the energy available at a solar irradiation of 1000 watts per meter squared, both on a daily basis and an annual basis. So taking Montreal, Canada as an example, we see that the daily GHI is 3.5 kilowatt hours per meter squared day. Converting this value to watts and dividing it by 1000 watts per meter squared, we obtain 3.5 peak sun hours per day. Referring back to the tables, we can see that we calculated the same value as the average value listed in this table using the global horizontal irradiation map. Continuing with our example, let's use the number of sun hours available per day in Montreal during the winter as indicated in the table. Recall that the PV system energy output required was 12.5 kilowatt hours per day. And note that the number of hours of peak sunshine per day in Montreal during the wintertime is 2.3 hours. We can calculate the PV power required by dividing the PV energy output by the number of peak sun hours in the winter. This gives us 5.4 kilowatts. Now we must take into account the losses found in the overall system, including those due to the conversion of direct current into alternating current. We do this by taking into account a number of derating factors. To do so, we multiply the Pmax of the solar module by these factors. These are shown in the table below, along with the standard value used for each one and the typical range used for each factor. On the far right, you have a more detailed explanation for each factor which you may find in the notes you downloaded at the beginning of this course. The factors are PV module nameplate DC rating, tilt factor, inverter and transformer, mismatch, diodes and connections, DC wiring, AC wiring, soiling, system availability, shading, sun tracking, and age. Multiplying all of these D rating factors together, we obtain an overall Pmax multiplier of 0.74. This means that a module having a rated capacity of 100 watts, for example, would in reality produce 74 watts because of the losses found in the system. Returning to our example, we can calculate the PV installed capacity by dividing the power required by the overall D rating factor. This gives us 7.3 kilowatts. The third step in sizing a PV system is to choose a module and correct its Pmax to the actual operating temperature. Here is a sample commercial module specification sheet for modules manufactured by Canadian Solar. Their nominal max power, or Pmax, is 285 watts, measured at 25 degrees Celsius. If we look under the temperature characteristics of the modules, we find the temperature coefficient, Pmax, and the nominal module operating temperature, or NMOT. These coefficients allow us to calculate Pmax under the operating conditions, that is, when the module temperature equals the NMOT, or the nominal temperature. The power output of a solar module can be estimated using the following equation, where delta T equals the temperature increase compared to the standard conditions of 25 degrees Celsius, and A equals the temperature coefficient Pmax with units percent per degree Celsius. In this case, the temperature coefficient Pmax equals minus 0.39% per degree Celsius, and the nominal temperature NMOT equals 43 degrees Celsius. So using the equation, we obtain a Pmax at 43 degrees Celsius of 265 watts per module. Let's take a moment to discuss the NMOT. In reality, the modules operate at higher temperatures and slightly lower solar irradiation conditions than those used in standard tests. And as we have just seen, the NMOT is used to determine the power output of the solar module. The NMOT is measured under the following conditions: solar irradiance of 800 watts per meter squared, an air temperature of 20 C, a wind speed of 1 meter per second, and a mounting with an open backside. From this definition, we can see that the cell temperature varies according to solar radiation, ambient temperature, and module cooling. The graph on the right shows the difference between the cell temperature and the ambient temperature on the y-axis, at different irradiation levels for a well-cooled module, a poorly cooled module, and a typically cooled module. The data presented is for a wind speed of 1 meter per second. The temperature of the module will be lower than shown in the figure if the wind speed is greater than 1 meter per second, and higher under calmer conditions. The following formula can be used to estimate the temperature of the cell, where the NOCT is the normal operating cell temperature in degrees Celsius, and S is the irradiation in milliwatts per centimeter squared. Here's a closer look at the graph. The red line represents a poorly cooled module, the black line shows typical data for an average module, and the blue line is for a well-cooled module. Now back to our example. Now we're ready to calculate the number of PV modules required. To do so, we divide the PV installed capacity of 7,300 watts by Pmax, which we've corrected for the actual operating temperature, or the NMOT, in this case 265 watts, and we obtain 28 modules. Recall that efficiency is Pmax divided by the product of the standard solar irradiation and the collector area. So if the efficiency increases thanks to a higher Pmax, fewer modules will be required. And if the efficiency increases thanks to a smaller collector area, the installation will become smaller. Researchers are constantly working to improve the efficiency of solar cells. Each new wave of solar cells gives rise to a new generation of photovoltaic devices. Today, there exist 3 generations. We will learn more about these in this course. Now that we've seen some basic calculations and understand efficiency, we think the time has come to ask the question, what different types of cells exist today and how efficient are they? Find out in our next video.